Hi, everyone. We're going to be talking about instrumentation today. Instrumentation is incredibly important in radiation safety because humans have no senses to detect ionizing radiation. We need to rely on these instruments to give us information as to, a hazard level of a certain situation. You need to understand how the instrument works, the type of radiation it's capable of detecting, what the values it's giving you mean, if there's any modifying factors that you need to account for. It's a pretty complex issue. It's not as simple as putting something on a scale and reading the weight. It's a little bit more complex just because of the roundabout way of deriving some of these values. So this chart we've discussed before. Just a refresher on it. This really goes into the various units of what we would be trying to track through instrumentation to really assign a sort of risk level to a potential person. So you have a source, or in some cases, radiation producing machinery that emit this radiation. But for radioactive materials, you have the Curie or the becquerel as a unit of activity. That exposes the air. You ionize air. And so the Rankine or the coulombs per kilogram of air are a measure of the ionization of that air. This is where we most commonly take measurements, just because it's much easier to have a gas-filled detector that closely mimics air, as opposed to taking direct measurements inside patients or using what we call phantoms to mimic a measurement that's directly inside of a person. There's give and take for which one is appropriate in which situation. But yeah, most of our instruments measure exposure. We say dose rate meters, but they're truly exposure rate meters. Now you get to actual absorbed dose. There are means of measuring absorbed dose. You have what are known as tissue equivalent detectors. So they kind of mimic the chemical makeup of tissue. And from there, they're able to measure the dose that is absorbed in that material. And so they would read out directly an absorbed dose. Or there even are some dose equivalent meters, which make that conversion from rad to rem. But over the many, many different types of detectors, there's a couple of different ways that you could sort of divide the function of detectors by radiation type, whether they're permanently placed somewhere, or portable. We need to use both for different reasons. And finally, just what they're actually measuring. They can be measuring the exposure in air. They could be measuring a water sample. They can be measuring a patient sample. They can be measuring a certain location. So there's many, many, many different types of instruments. So we'll go over the main ones that we use in a hospital setting. Okay, so we have portable and installed instruments all around the hospital. Generally, for a portable instrument, what do you think you would need? You would need something that can be portable. You need to be able to pick it up. It needs to be able to handle a little bit of abuse. These things get knocked around in day-to-day use. Sometimes they're going into, construction areas. So they're not as accurate. They're not as repeatable, but they give you immediate results. You can take them to where you need to go and you get instantaneous feedback, which in a lot of situations is desirable, if not absolutely mandatory. Now, certain situations you may want to have a more precise count. You can use your portable instrument to get an instantaneous reading in the moment, but then you want to take some stuff back to a lab for further analysis. So that's where you would bring samples, whether they're wipe samples, actual physical material samples. You would just make sure you have a good means of keeping them organized until you can bring them back to the lab, at which point you can run them in these much, much larger pieces of equipment that will give you better counting, but it's after the fact and it's a little bit more time consuming. So what are we actually measuring? There's lots of different values that we're looking to measure through these instruments, through the measurements from these instruments. From something like activity, we have meters or equipment in the nuclear pharmacy that their sole purpose is to calculate activity. It's very important when you're going to be distributing a dose to a patient. You want to know exactly what that activity is. A lot of these doses come from the commercial pharmacies already calibrated, but we definitely do a secondary check just to make sure that what they say is there lines up with what we expect. That's very basic due diligence. It's not a very time-consuming step, and it definitely can save a lot of headache down the road for a patient that gets the wrong dose. But you can also use that to measure, you got activity, you got concentration, which is essentially just activity per volume. We got the exposure rate meters, dose rate meters, and even dose equivalent rate meters. I sort of mentioned this, that you have the passive versus real-time meters. You guys are already wearing dosimeters. Those are passive. You wear it, and it eventually gets read, and it becomes part of your permanent record. But in the moment of receiving that exposure, receiving that dose, it's not really giving you any information. So it's definitely an after-the-fact thing. You could send it out immediately for an emergency read, and you'll get a value back pretty quickly. But as far as needing information now, dosimeters sort of fail at that. We have area monitors where we essentially just hang dosimeters up on a wall. We have, we collect samples in certain forms all around the Institute that are just not giving us a result immediately. And that's versus, the portable meters or like electronic dosimeters. Those are actually little dosimeters that have a digital readout, and they tell you that in real time. But they're a little bit less precise. So we say that when you're wearing an electronic dosimeter, you also want to wear your actual dosimeter, because that's the one that's your permanent dose record. Whereas an electronic dosimeter is solely for, some guidance in the real time moment. We also break down detector types by the actual physical makeup of the detection volume. You have these instruments. There's lots of electronics, handles, packaging and stuff, but there is essentially inside there is some sort of detection medium that is sensitive to the radiation you are trying to measure. So one of the most common are gas fill detectors, and there's a number of different types that we'll go over individually under that gas fill detector heading. Depending on the fill gas, the voltage you supply to the detector, all of these change the way that they measure the actual radiation. There are also what are known as scintillation detectors. These are essentially crystals that are sensitive to radiation in one form or another. So those are used in a different type of setting. A solid crystal is very dense compared to a gas-filled volume, so they have different benefits in that regard. And then there's other less used types of detectors, like semiconductor detectors. Those are useful for if you need a very, very, very physically small detector. Those are going to be what you use. And then finally, just something like film or other dosimeter materials. We use OSL dosimeters, but there are other technologies that are perfectly adequate. We tend to use the OSLs because they are a nice balance of convenience and accuracy. So we'll jump into the gas fill detectors. So really, as the gas fill detector implies, it is a closed volume that has a fill gas, whether that's air or some other type of gas, is detector specific. But ultimately what you have is you have a volume with the actual detector wall being a conducting material. That would be the cathode. And then you have the anode is just a wire that runs through the center of that volume. You have some sort of voltage that goes across this volume. And depending on the level of that voltage and the incident radiation, you get a number of different sorts of interactions that can be useful in different realms. And that's where this curve that you have here, this is the gas fill detector curve, and proportional to the voltage applied and charge collected dictates how that meter actually reads out what it's capable of reading and how it's used. So we're going to go through each of these regions. You see that there's a number of regions that are indicated here, but really only 3 usable regions when it comes to actually taking these measurements. You have the ion chamber region, the proportional counting region, and the Geiger counter region, or the GM region. Those are the 3 that are used, and we'll go through them one by one. It's worthwhile because this is the basis of, probably 90% of the instrumentation that we use in the hospital. So going to the first region, that is the ion chamber region. You can see that this is the lowest voltage region. And so the reason that there's low voltage is that those actual ionization events that happen inside that gas volume, every single event is collected, and it's happening at enough of a frequency that the individual charge collections are happening frequently enough that you actually get a detectable charge. It's a very, very faint charge, but then you have sensitive electronics inside of this meter that allow it to actually measure that charge, that voltage going across, and it can give you a dose rate. The more ionizing events that happen in that volume means there's more charge, and that means that there's more radiation present. So it will give you a higher reading. So an ion chamber is our choice of instrument when we are going into an area that we know has radiation present. If you know there's radiation and you want to quantify it, an ion chamber is your instrument of choice. It's not particularly sensitive at very, very low levels. That's true of most ion chambers, at least as compared to some like a contamination meter like a GM. You would not use an ion chamber to find loose contamination. It's really only if you know there is something there. Now you can get down to lower and lower levels, like on the order of background levels, by pressurizing that chamber. So you have a gas fill detector. If you increase the pressure, if you stuff more gas molecules into the same volume, you have a higher and higher pressure. What this achieves is more gas molecules inside of a same volume means that there's more of a chance for radiation to interact with those gas molecules. So the higher chances of interaction mean that you will see lower levels of ionizing radiation. So some of these are pressurized. Some of them are not pressurized. They're perfectly adequate instruments, but when you want to see that low level that's barely above background, you'd want to use a pressurized ion chamber. The next region on this curve is the proportional counting region. So that is this curve right here. And you can see that there is a divide between these two lines as they increase. And that's where you get the term proportional. Because unlike the ion chamber, there is an actual multiplication factor. So you have one ionizing event that happens inside of this gas volume. And because you have a higher voltage, a higher, electric field across this gas volume, those ionizing pairs are pulled to their respective poles. But the more voltage means they're pulled with more force. They're actually pulled with enough force to create more ionizations. And so that is what we call an avalanche. So you have one ionizing event that triggers these two ion pairs to start being pulled by the electric field, because the gas molecule unionized is neutral. But as soon as you ionize it, that means you strip an electron from that molecule, and suddenly you have a positive molecule and an electron that are both charged. So those will go their respective directions, and if they go with enough force, they will collide with other molecules in that volume and actually ionize those, creating that avalanche effect. Now, in a proportional counter, it is a proportional avalanche. It is not a full-scale ionize everything avalanche. That's what happens with GMs, which we'll get to. For this, it is a very calculated multiplication factor. And the reason for that is that these detectors are very useful for discriminating between alpha radiation and beta radiation. So there's situations where you want to know if contamination is an alpha particle or a beta particle. It's useful because there's different limits for contamination for these two types of radiations. Alphas are more biologically damaging, significantly more. So there's lower limits for acceptable contamination. So if you're in a facility that uses alpha emitters, you want to be able to quantify those specifically and separate them from any sort of beta signal that you have, in order to know that you are in compliance with the regulations and you are on top of any alpha contamination that may exist. And so the way that they do that is you set a threshold voltage. So alphas versus betas, think about just inherently what they are. I know we're going back a couple months now, but an alpha particle is a large, heavily charged particle. It's two neutrons, two protons. So it's much, much bigger than a single electron. So it's got the mass and it's got the charge. So if an alpha particle interacts with your detector, it is going to create a much larger signal than a beta particle. Just there will be a lot more interactions before it loses all of its kinetic energy. So the way that you can discriminate between alphas and betas is that you can set a threshold voltage that will only see alpha particles because they create such a dense ionization in that detection volume. You can get away with a lower voltage that the alphas will be seen, the beta particles will not be seen. So if you set it at this voltage, and this voltage is decided through a calibration, we send these off to a vendor. They give us the correct voltages for this discrimination. But ultimately, you can set a voltage where you will only see alpha particles. So that gives you an alpha count. And then you can increase that voltage to a point where you will see alphas and betas. So if you have these two measurements, you can subtract the alphas from the alpha beta count and then have your beta count as well. So this is useful very much for contamination surveys, for compliance in areas where we're doing alpha therapies and the like. Okay. Oh, I got ahead of myself. Yeah. So this is how it achieves the alpha beta discrimination. And yeah, if you can set your threshold somewhere between the peak of a very energetic beta and the lower peak of an alpha, or the higher peak of an alpha, you can get a very successful discrimination. And that's predominantly why these are used compared to other meters, because a lot of these proportional meters, they actually have to have an attached gas tank. They're complex machines that need to be set up. They need to be charged before use. They're a little bit complex to use, but that ability to discriminate is unique to them. So they are tolerated because of that feature. Okay, and that brings us to the GM, or the Geiger-Müller tube. So this is the highest point. Let's go back to that chart just so we can know where we're at. So we're in the GM range, and you can see that increasing voltage, you hit a plateau that is considered this GM range. If you go past it, you actually create such a strong electric field that there's just spontaneous ionization, and you would just have a meter that is just going wild. You would not get counts because it would just be in a continuous discharge point where you would never be able to actually detect something because it would always be clicking. Going back to GM. So these are the highest voltage detectors. So what happens here is that really any ionizing event that takes place within the active volume of this detector, remember it's still a gas-filled detector, creates that ionization, creates that cascade, that avalanche effect. But because the electric field existing is so high, it actually ionizes. These avalanches are like continuous until it actually ionizes the entire volume of the gas. So that's why you don't have any sort of discrimination. You don't know what your count was. You get counts from this meter, but you don't know if it was an alpha particle, if it was an electron, if it was a photon. That was the actual ionizing event. All you know is that there was a count. So you can get a lot of information from these detectors, but these are amongst the most sensitive detectors that we have. You can see individual decays with a meter like this. So these are incredibly useful for contamination control. In all the labs, they have at a minimum, they have a GM that will let them see alphas, betas, photons. So it's as close as you get to an all-purpose meter, but there are significant limitations if you try to use it beyond a contamination meter. But it is a useful meter. Now, GMs suffer from the issue of what's called saturation. And what that means is that we'll start with the dead time. So because every count essentially ionizes the entire volume of the detector for a very brief microsecond, in that period of time, the meter is incapable of registering another count, another ionization. So there's what's known as dead time. And as your count rate gets higher and higher and higher, this dead time becomes more significant. It gets to the point where you might be missing more counts than you're getting. And there's ways to correct for it, but ultimately at that point, a GM is probably not the meter you want. If you're in that high, that intense of a radiation field, you're going to want an ion chamber that can actually better handle the onslaught of ionizing events. So that's where the saturation comes. You hit a point where there's so much radiation that the meter never actually gets a chance to calm down from that the previous ionization event. And so you get to this point where the scale goes up. It goes really fast, and then it just drops to zero. And that's because the system's just been completely overwhelmed. If you didn't have experience with these meters, you could think that, oh, the radiation stopped, this is fine. But you should know that means that you're actually in a very high radiation field, and you need to get a better meter and probably get out of there. Some meters have like electronics to try to mitigate this effect, but honestly, if you're using a GM in a situation like that, you should try to get your hands on a better meter. Also, these meters are very energy dependent. If you're trying to do dose rate, as I said, these are contamination meters. These register clicks or counts. You really don't want to try to get dose rate with them, because they're, depending on the energy of the radiation they are detecting, they can give wildly different dose rate estimates. You know, you can be off by a factor of 100 or more. So if you're trying to quantify radiation and you have a meter that is incapable of being accurate to less than 100 times, it's essentially useless. Like the difference between 2 MR and 200 MR per hour is a pretty big difference when you're talking about safety. So it's why that we never use these meters for dose rate readings. Okay, now so we're out of the gas fill detector region. We are into scintillation crystals. These are the solids. So scintillation essentially means light. That means that when this radiation interacts with this crystal, it creates an actual flash of light. It's a very small flash of light, but if you have sensitive electronics that are optically coupled to this crystal, this little flash of light hits what's called a photocathode, and that flash of light creates an electron. And so you have, individual electrons. They're not enough to register a signal in any sort of electronics, but you have this photomultiplier too that takes that electron and it multiplies it. And it multiplies it exponentially. So, you go from a couple electrons to a couple hundred to, tens of thousands to eventually, you get millions of electrons, which is enough to actually be an electric signal. And that is what is counted. That is, gives you your count rate. So the first time you click on a scintillation detector, the first thing you'll notice is it has a very high background level. You'll hear a lot more clicks than you would with something like a GM. Like a GM, you expect 30 to 50 counts per minute just from background sources of radiation. For a scintillation crystal, you expect about 300 to 500. So, on the order of 10 times more counts per minute, just because it's more sensitive to the energy of typical background radiation. It's more sensitive to photon radiation. Again, you have a dense crystal, much more likely to interact with a photon than a gas fill detector. Gas is not a very dense, form of matter. So the crystals are going to be much better at seeing things like low energy photon radiation. And that's actually the main focus of where we use these instruments, for seeing some of our sources that are very low energy radiation. So these are a crystal. It mentions here that they are hygroscopic. That means that you really, if they're ever exposed to ambient temperature and pressure, they will turn to mush. They need to be free of any humidity in the air or anything like that. They're incredibly sensitive, incredibly delicate, but they're usually sealed in some form to prevent that sort of thing from happening. Okay, yeah, so we covered all this stuff. And so the common crystal for scintillation detectors is sodium iodide, but there are lots of other crystals that are used. Scintillation crystals actually make up the core of what's known as a spectrometer. So a spectrometer, most instruments we have detect radiation, and they tell you it's there. They quantify it. But a spectrometer takes it a step further, and it actually can tell you the energy of the radiation that's interacting with the crystal. And so these are, like I said, they're scintillation detectors. They're crystal based because when a photon interacts with a crystal, the amount of light that it produces will be proportional to the energy deposited in that crystal. So if you have photons that are losing all of their energy in that crystal, you will get a good idea of the energy of that photon, because these interactions are taking place very, very quickly. So you get these flashes of light that are of varying intensity. What a spectrometer can do is measure the intensity of that light and then sort of bin it into, okay, one count was at this intensity, one count was at this intensity. And pretty soon with, radioactive material sources, you'll get a lot of counts in a single energy bin, because that is the energy of the radiation being released from the source. You don't have scatter. Some of the photons won't put all of their energy in the crystal. So what you'll get is a pretty wide peak. But the center of that peak should correlate to some sort of characteristic energy for the isotope in question. And that's a very useful way for us to actually find out what something is. We have portal alarms around the hospital that alarm when there's radiation present, but they don't give any more information. We might need to know what isotope is in that bag that set off the portal alarm, whether, if it's a long-lived isotope or short-lived. We need to know how to dispose of it, where to dispose of it. So it's very useful to be able to ID the energy of the radiation coming off of these unknown sources, because that will allow us to actually take an educated guess as to what is causing the alarms. So I mentioned that we have, portable versus fixed systems. A couple of the lab pieces of equipment that we have, these are two of them. This is a gamma counter. So this is another one of those scintillation detectors, except it's a much bigger crystal, much more expensive because it's a bigger crystal. And it's also not just like a disc, it's actually a well of sodium iodide. So the sample goes inside of that well, which means that you have a detector that is completely surrounding your sample. Something that you have to deal with when you have a handheld detector is that essentially you can put it up to a source. If you are touching the source with that handheld detector, at best, you will get maybe half of the radiation that's coming off that source, because half of it's going in the other direction. You assume that is half. It might not always be exactly half. But so the best you're going to get is maybe a 50% efficiency, and that's assuming everything else is running perfect. But if you have a system where you can actually place a sample inside of that crystal, then at least from a geometry standpoint, you have almost complete coverage of that sample. You'll get more of those counts, more of those, the radiation coming off of the sample will be counted. Other benefits, the sample stays put. You're not shaking your hand, so you have a more fixed geometry. You can count samples for hours. You can count samples for very, very long times if you need to get to very, very low, very, very high certainty that what you have is a positive count versus just a natural, fluctuation of variation in this equipment. So these systems usually have better detectors. They allow for longer count times that give you a more confident result. This is actually a liquid scintillation counter, similar to a gamma counter, except instead of having that sodium iodide crystal that is the detection medium, you actually put in what's known as a liquid scintillation cocktail. The scintillation medium is in the cocktail itself, along with some pretty harsh solvents. The idea being that if you take a wipe of a surface, you can get some of the contamination there. If it's present, you will wipe some of that off. You put it in the sample. This liquid cocktail comes into direct contact with the sample. The solvents pull it off of your wipe medium, and then there's a direct contact between the isotope that's in suspension and the scintillation medium. Whereas most other detectors, that radiation has to pass through something before it's counted. And in the case of very, very low energy radiations, if they have to pass through something, there's a good chance that they won't be counted. A classic example is tritium. Tritium is an incredibly low energy beta emitter, to the point that no handheld instrument is going to be able to detect it. A GM can't detect it. You can't use any handheld instrument. So what you're forced to rely on is taking wipes. You have to take wipes of the area that you're working, and then you have to run in a liquid scintillation counter, because that's the only detector where there is direct contact between the sample and the scintillation medium. And that's why these are very important to have, especially if you're working in a lab with tritium. Another type of specialty measurement that we take is referred to as a bioassay. So the purpose of this is to measure a potential uptake or intake of radioactive material that got inside someone's body. Now that could happen in the labs through someone, using something like radioiodine. You use that on a bench. A certain amount of that is volatile, which means that it'll just sort of sublimate off of a solid source and you can breathe it in. And when you get iodine in your body, it goes to your thyroid. So this is an example of a thyroid counter that just takes a very large sensitive probe, holds it up to your thyroid, and sees if there's counts above background, and then you can assign a dose to that. Other possibilities are urine samples. You can count someone's urine after an exposure event and use that to quantify the potential, body burden of certain isotopes. But there's a lot of factors that go into this, because you can't just hold a meter up to somebody and say, oh, like there's this many counts above background, you have this dose, because you have to figure out, okay, well, when did it happen? If I'm taking this measurement an hour after the exposure event versus a week after the exposure event, that means that the quantity that was once there is significantly different. If I'm getting counts a week after an exposure event, that means that on day one, there was a lot of material that got into that person's body and has stuck around and has given them dose. So that's why we need more information besides what the meter is telling us in order to really monitor this type of work and to actually assign doses to certain situations. So right now, we really only do bioassays for people that are using radioiodine, because that's a very controlled material. We also use that a lot in the clinic. So we have therapies that involve huge amounts of radioiodine. We ask that, nursing staff, even the physicians, after they do therapies like this, come down and do a thyroid scan just to make sure that there's not any sort of uptake of this iodine that's going to the clinicians that are taking care of these patients. Thankfully, the only other bioassay we'd have to do is if there were more tritium users, is we would be collecting people's urine and counting it in liquid scintillation counters, because again, that's the only way to detect tritium. So that's what we'd be forced to do. Thankfully, you need to use a lot of tritium before it rises to that threshold, and we don't have people using that much. So we are not yet required to monitor people's urine. Oh, so I got ahead of myself here. So this is the spectrometer that I was talking about. Generally, these are sodium iodide detectors because they're the cheaper ones to create and to use. But yeah, you can see this is an example of a spectrum. So you can have a couple of peaks here. You see some background noise and then just a couple of peaks. And depending on where that energy falls, you can make some pretty educated guesses at what type of isotope it is. So this has a 364 large peak. I know that this is iodine 131 because that's a very abundant decay with that isotope. You have other energies, but they're much lower abundance. There are what are called HIPG detectors. They're high purity germanium detectors. These will give, this is a pretty thin peak. Sometimes you have peaks that are very broad. Sometimes you have peaks that are very broad, something like this, where it's not as clear cut. Something's there, but the energy and everything, it's a little harder to ID. But for the high purity germanium detectors, you'll have essentially a single line. It's incredibly clear as to where those peaks are. The problem with them is that the only way they work is in incredibly low temperatures. So you need to have one of these detectors essentially immersed in liquid nitrogen. That's how they are used. A lot of them, if they come up to room temperature, the crystal will be, irreversibly destroyed. So it's a big deal to keep these instruments maintained, keep a stock of liquid nitrogen for them. But in terms of their ability to ID, isotopes, they're irreplaceable. You need to have one of these if you're working in some sort of QA lab where you have to make sure there's not contaminants and such. I'd mentioned that we run into situations where we have waste frames that go off. You have alarms. So it's one of our responsibilities to keep radioactive materials from entering our general waste stream. And that's a challenge. That is a challenge when you have a hospital with patients. Essentially, once we put something in a patient and they're released, it's no longer licensed material. However, regulators don't really see it that way. So we always have to answer for anything that comes out of our facility and then gets flagged. There's lots of waste transfer sites where material is, put from one truck to another before its final destination, wherever it's going to go. A lot of these facilities have large radiation detectors to make sure they're not trucking in radioactive items. They also have means of knowing where the waste came from when they do go off. So our goal is to make sure that anything that's going to set those alarms off sets off on-site alarms first. So we have these waste frames that are around portals, or the portal frames, to minimize this the passage of this material, or if it doesn't get segregated prior to reaching the waste stream, this is sort of a last-ditch effort to make sure that they do not get out. If it's gotten to this point, there was another failure along the way, but just as a double check, we make sure that we can stop most of these materials before they leave the facility. And we do a very good job at it. It's very rare that we have something that gets out, and the regulators appreciate that. So neutrons. Neutrons are difficult to detect because they are chargeless. So you need to sort of detect the evidence of neutrons versus the actual neutron itself in a lot of meters. So you have a lot of meters that are surrounded by large amounts of plastic. Neutrons, the way they're stopped, you figure the size of a neutron is roughly similar to a hydrogen nucleus, because hydrogen is simply one proton. So if you have neutrons, high energy neutrons in, say, like a LINAC vault that is covered in lead, they'll bounce off the lead, but because the lead atom is so much bigger, they'll bounce and just keep going. They won't lose a lot of energy. But if you have a lot of hydrogen present in something like water or plastic that has high hydrogen content, they actually bounce. They hit those hydrogen atoms and they lose their energy. And so they get down to a lower energy. And it's only those low energy neutrons that can then interact with a detector and be counted, essentially. So most detectors have some form of moderator with a detector inside of them. Each one of these big balls has a tiny little detector in it that actually counts the neutrons. Another difficult aspect of neutrons is that their energy dictates how harmful they are. So if you want to know the energy of the neutron present to be able to figure out how much of a hazard it is, be able to know if you're within the regulations for instantaneous dose rates, because high energy neutrons of certain energies are going to have a much higher radiation weighting factor than other energies of neutrons. So that's a challenge. That's why you have like a detector like this that has many different sized plastic balls, because the detector, something that gets detected on the small one but not on the big one, you can make guesses about the energy range of the neutron for that interaction. They're all imperfect. It's another one of those situations where you have to get the best measurement you can. You're not going to get anything perfect, but that's something you have to accept anytime you pick up a radiation detector, is that it's just a different animal than something like any other lab equipment, something like a thermometer or a scale. Those are just so much more precise than anything you could ever hope to get in terms of measuring radiation. And finally, dosimeters. Dosimeters are the quintessential example of a passive detector, but there's many different types of dosimeters available. There's many different designs in them to make them as functional as possible, because a dosimeter is supposed to display your deep dose, your shallow dose, your lens of the eye. It's supposed to have some information about the energy of the radiation. Your guys' dosimeters have a neutron chip in them to detect neutrons as well. That's very important, because we'd want to know if the RTs are being exposed to neutrons. That's something we'd want to know right away. And then just the actual holder, the makeup of the dosimeter is also a important consideration. So, for example, alpha emitters, they'll be stopped by a thin piece of plastic. So our dosimeters are not going to measure alpha exposure, but we know that, so that's not a big deal. But you can have dosimeters that have different types of materials in them, and so you have an exposure that gets through, say, a little over 1 millimeter of copper, but then doesn't get through the lead. You can say, okay, well, I know that photon was this energy then, compared to, got through a very thin copper foil. It's the low energy stuff will get through the smaller foils, and that's useful again for knowing the energy of the radiation, because the energy of the radiation is important to know if it gives you shallow dose versus deep dose. If it's a very low energy radiation, it's not going to get inside your body very well, so it'll only be a shallow dose. So there's fancy algorithms that can figure out the breakdown of the dose based off of these filters, but that's why they're used. Film is the most basic filter the most basic dosimeter that there is. It was the first dosimeter ever to even be thought of. You have scientists that, right after the discovery of X-rays, the discovery of inherent radioactivity, they realized that there's potential for harm, and they started carrying just undeveloped film on them. And what they would do is that at the end of the day, they would develop it. And it wasn't really a quantitative check, but if there was, very bright developed, they would know that they got a lot of radiation exposure versus, a darker exposure, meaning they got less. That evolved quickly to a point where they could have some form of quantitative evaluation, but that really dawned the era of dosimeters and people recognizing that you need to measure this stuff. There's fancier versions now, the TLD and the OSL, the thermoluminescent dosimeter and the optically stimulated luminescent dosimeter. Those are fancy ways of saying that this one, you wear it, you give it back to the vendor, they heat it up, and when they heat it up, there's an output of light. The magnitude of that output of light is proportional to the radiation you received. For an OSL, you wear it, send it back to the vendor, they shine a laser at it, there's an output of light, and that output of light dictates the magnitude of that light dictates the dose that you receive. So they behave in much the same way. TLDs can be physically smaller. So you'll see on ring dosimeters that we hand out, they're actually TLDs, and the whole body dosimeters we hand out are OSLs. So that's how they work. It's important to measure efficiency. I had mentioned efficiency in terms of the flat detectors versus the well detectors. But you'll notice that every instrument has an inherent efficiency for a certain energy radiation. You can make charts like this that show about what efficiency you would expect for certain energies. This is for a GM. A 44.9 is a type of GM. So you see that when you get down to that tritium range, just not going to see it. But then you can get up to a point where you have very high energy beta particles. These are going to be very efficiently detected. So it's very important to have an idea of what the efficiency is for the isotope you're using, because that allows you to make a quick estimate as to what's actually there. If you take a measurement and you get a couple hundred counts and you have a 50% efficient meter, that's a very small spot of contamination. But if your meter is incredibly inefficient, sometimes that small bit on your meter can actually be a much larger issue that you're just not realizing your meter is just not good at seeing. So I mentioned that a lot of these instruments are contamination instruments. So really they read out in counts per minute. That efficiency is what gives you disintegrations per minute, and that's really what we want to know. We want to know the activity of what's there, not what's being detected, but what is actually present. So the calibration process for these instruments is what lets you establish an efficiency, make sure that they're seeing what they need to see, making sure the scales work. There was a question posed on the last one of same for low activity and high activity. Going back to the GM side, we know that at high activities, you actually lose some counts. There's some dead time. There's some saturation where you actually lose counts. So they're not going to be the same efficiency. The higher count rates, the higher activities are actually going to be lower efficiency because you're missing more counts. There's this idea of minimum detectable activity. You want to know the lowest level of what your instrument is capable of seeing, because if you have a meter that's a background of 30, 40 CPM, so it's okay, and then you measure a spot and you get 60 CPM. So is that real? It's above your background, but if you've ever turned on a GM, you'll see the scale like just kind of fluctuating. It never stays still. So it's very difficult to know what's real versus what's not real. You need to have some sort of statistical benchmark to say one versus another, and that's where this fancy equation comes into play. It's really just, there's a constant that's your level of confidence that you want, but really it's based off of the background rate. If you're in a high background area, you're going to be able to see less, but if you're in a low background area, that you're much more likely to have those counts actually be real. And the efficiency comes into play as well. So we use this a lot, just evaluating pieces of equipment to make sure that it will see the levels that we need to see in order to be in compliance. So we use instruments for releasing waste. We talked about waste and how we deal with it. If you decay it on site, you want to make sure that when you release it, it's indistinguishable from background. So you need to have a meter that's good at seeing background. So something like a sodium iodide detector has a pretty high background count. So you would expect to see if there's any lingering above background. You can actually take a sodium iodide and hold it up to the decayed waste. And whether it's high energy or low energy, it should be able to see it pretty well. For dose rate meters, the regulations say it needs to be able to measure from 0.1 to 1,000 millirem per hour. That may be a little bit outdated because we have therapies that go above 1,000 millirem per hour. Our meters that we have go up to 50 R per hour, and they're calibrated to that range, but that is outside of the regulations. It's kind of going above and beyond just because we know that that's what we require for our group, for our hospital. And so we make sure we can do that. So just understand that anytime you're going to pick up an instrument, you need to consider what you're trying to achieve with it, what you're trying to measure, what isotopes are going to be present. If it's a radiation producing machinery, that dictates the type of instrument you need. Know how intense the radiation is, know the calibration schedule, know a couple of pieces of information that are discovered at calibration, like the efficiency. You should have that in the back of your mind, and be prepared to recalibrate. We calibrate yearly, just to make sure that these instruments don't drift over time, that we can be confident that the results we're getting are accurate. And so these are just a couple of charts we'll go over more in person, but I talked about how the energy dependence of certain meters. So you can see this is an ion chamber. So you can see that according to the energy, you could expect to be off by a factor of 20, 30, 50% or more, especially in the low energy range. These meters have a slide that you can physically open to sort of mitigate the worst of those effects. But you see, you're not off by a lot. You're off by, generally in the most common range, off by 20% or more. Not much more than 20%, I should say. Same for this meter, again, out of that very low energy range, you're pretty much in the plus or minus 20% range. One of these meters that we have, this is actually a micro REM meter. So this is one of those meters that reads out in REM. It's not actually a gas field detector. It is a tissue equivalent scintillator. So it's a sort of plastic that has a roughly similar chemical makeup to tissue, a lot of hydrogen, carbon atoms and stuff. But this gives you a very flat response. So these are useful for us. And then compare that to a GM, where you'll see that it's not, 10, 20%. It's 2 times, 3 times, 4 times, 5 times. So you could be off by, an order of 5, 6, 7 or more, depending on the energy. And then take that to the scintillation detectors, and you'll see that they can be, these are the ones that at a bad energy, at an unfavorable energy, these can over respond by 100 times or more. So you'll get calls from the pharmacy, from researchers saying, "Oh my God, I found a spot of contamination that's 100 MR per hour. Like, should I clear the lab?" It's like, okay, well, calm down. What instrument are you using? Okay, chances are that it's not as bad as you think it is. we'll bring over a dose rate meter, and you get over there, and sure enough, it's a couple MR per hour, which you know is big for contamination, but it's not the disaster scenario that you're sometimes presented with. So that's why it's important to know the instrument you're using and know its limitations. And that's it for instruments. We will go over them in class, and I will see you guys on Thursday.